This video wraps up the hypothesis testing series by focusing on some important odds and ends. First, I want to emphasize what statistics is and isn't. It can be thought of as a set of tools to help researchers to make decisions in the midst of uncertainty. Researchers make decisions about unknown population values based on sample data, by basing those decisions on probability. But we can't prove anything with statistics, because we don't have all the data. All we can do is find evidence against the null hypothesis, that is, disproof. For example, we can disprove a hypothesis that states that there are no white crows by finding one white crow. But we can't prove that there are no white crows unless we find all the crows. Proof versus disproof is an important point. In 2005, the ADA News reported a study that found no adverse neurological effects for amalgam. The null hypothesis was that amalgam exposure does not produce adverse effects, but this cannot be proven. Instead, the researchers found no evidence against the null hypothesis. That is, they found no link between amalgam exposure and abnormal neurological signs. This is absence of proof, not proof of absence. This is one of the reasons that it is difficult to discuss the safety of fluoride with anti-fluoridationists. They want proof that it's safe, and all that research can provide is absence of proof of potential harm. Researchers make decisions based on probability. Anytime they use statistics, they're dealing with uncertainty. This is a representation of how researchers make their decisions. The null hypothesis is either true or it's false. If researchers had the entire population of observations available to them, they wouldn't need statistics. They could just look at the real world and see what's going on. But they don't have access to the entire population. Instead, they draw samples from the population and then make decisions about the population based on their sample results. This means that there is always a chance of making the wrong decision. When the null hypothesis is true, there are two possible outcomes. If the researcher rejects the null hypothesis, she's made the wrong decision. She protects against this by setting the significance level, alpha. If the null hypothesis is true and she decides not to reject it, she's made a good decision. When the null hypothesis is false, there are also two possible outcomes. If the researcher rejects the null hypothesis, she's made the right decision. But if she fails to reject it, she's made a mistake. She protects against this false negative by setting the power of the test, the likelihood of finding a real effect. The power of a test is based on several factors, including sample size. Researchers always aim for one of these outcomes, and would especially like to be here, because they generally believe that their research hypothesis is true, and therefore they seek to reject the null hypothesis. But while this is where they would like to be, they never know whether the null hypothesis is true, and therefore they never know when they've made an incorrect decision. Confidence intervals provide an alternative to hypothesis testing. The focus is on estimating or providing a best guess at a population value. Suppose that a friend bets you that you can't guess the height of Mount Everest. One option would be for you to take a single guess at the height. Another might be to guess a range of values. Which bet would you take? The range of values gives you more of a chance of hitting the exact height of Mount Everest. You might still be wrong, but you have a better chance than when estimating using a single value. This is the idea behind confidence intervals. The researcher takes a sample value and then draws an interval around it in order to obtain a good estimate of the population value. The interval provides a better estimate than the value alone. The researcher would report a specific level of confidence in that interval. The most commonly used confidence level is 95%. Bazin et al. Used hypothesis testing to decide that there was a difference between the 5,000 parts per million and 1,100 parts per million fluoride conditions in the percentage of subjects with one or more primary root caries lesions that had hardened after 6 months. They also could have drawn a confidence interval to estimate the size of this difference. They would have started with the observed difference between the two groups, which was 28%. They would then have created a lower bound and an upper bound on this estimate. This shows what a 95% confidence interval would look like. They would estimate the difference to be as low as 14% or as high as 42%, with a higher percentage of patients with hardened lesions in the 5,000 parts per million fluoride condition. They would be 95% confident that this interval contains the true difference between the two conditions. There's no certainty with statistics. The confidence interval may not contain the real difference, but it is calculated in such a way that it will 95% of the time. Here's an example of both hypothesis testing and confidence intervals from an orthodontic study comparing plaque buildup for elastomeric and self-ligating brackets. This is part of a results table showing plaque accumulation after 3 months for the elastomeric group. The mean increase in area of accumulation on lateral incisors was about 24%, which was statistically significant. The 95% confidence interval estimates this increase to be between 10.56 and 37.62%. To summarize, statistics is a set of tools to help researchers make decisions by using probability as a basis for those decisions. Science moves forward on the basis of disproof, not proof. Researchers set up a research and null hypothesis, then seek evidence against the null. Researchers live with uncertainty. Statistical decisions are made on the basis of data collected from a sample, and samples fluctuate. They don't always provide an accurate reflection of the population. Confidence intervals provide an alternative to hypothesis testing. The purpose is to provide a best guess at a population value by creating an interval that has a high likelihood, usually 95%, of including that value.